You download the fourth semester syllabus for AI and machine learning and start scrolling. 6 distinct subjects, dozens of units, and hundreds of complex topics ranging from singular value decomposition to multiprocessor architecture. It looks like an impossible mountain of disconnected information. The common response is to fall back on the standard engineering survival strategy. Treat subjects AL 401 through AL 406 as completely isolated hurdles. You cram enough discrete math to pass the midterm on Tuesday, and then purge it to memorize software engineering protocols for Thursday. This semester marks the transition point, where generic engineering fundamentals end and your specialization in artificial intelligence begins. If you look at the course codes, this seemingly random list of 6 subjects is carefully designed. They snap together to form 3 distinct, interdependent pipelines. Mapping these connections allows you to move beyond simple memorization. It provides the framework necessary to build real-world AI applications, rather than just repeating theory. The first pipeline is the AI and Math core, pairing AL 401, discrete structure and linear algebra, with AL 405, machine learning. Students often want to jump straight into AL 405 to train predictive models and run neural networks. However, attempting this without the underlying math leaves you unable to troubleshoot why a model is failing or how it is actually processing data. This chart illustrates that journey. It shows how raw mathematical matrices are manipulated step by step until they form a trained predictive data model. AL 401 provides the linear algebra, the matrices, determinants, and hypothesis testing that allows the machine learning models on the right to function. Look at the matrix calculation node. When you calculate an eigen decomposition in math class, you are breaking down a complex matrix to find its core structural patterns. That exact mathematical operation directly powers the linear regression algorithms you study in your machine learning class. Mathematics serves as the internal logic that allows these machines to learn. Every algorithm in the ML syllabus is a direct application of the theorems found in your discrete structures textbook. The second pipeline is the logic and hardware layer. Here, we pair AL 402, the analysis and design of algorithms, with AL 404, computer organization and architecture. Algorithms teach you how to solve complex computational problems, like searching vast datasets, without wasting time or computing power. It is the study of efficiency. However, the speed of any algorithm is strictly limited by the physical hardware executing the instructions. Even the most elegant code will underperform if it ignores how the computer is actually built. This diagram breaks down that hardware reality. We see data moving from cache memory, fast storage near the processor, straight through the CPU's instruction cycle. AL 404 explains how these physical memory systems and processor architectures operate. Understanding how cache memory interacts with the CPU allows you to write code that hardware can process at its maximum potential. Mastering this layer distinguishes a high-level engineer from a standard programmer. The final pipeline is the builder level, combining AL 403, software engineering, with AL 406, the Java lab. A machine learning model is essentially raw code. Without a proper interface, that model remains trapped on a local machine, inaccessible to any actual user. The Java lab provides the practical skills to build graphical user interfaces and handle user events. It teaches you to connect back-end databases using JDBC, so your AI models have a functional environment. Software engineering provides the industry-standard protocols to manage the project. It covers how to map requirements, design system architecture using UML, and test the code to ensure reliability when the application scales. These 2 subjects transform abstract math and optimized logic into a deployable commercial software product. They provide the shell that makes your AI usable in the real world. This isometric diagram shows the complete stack you are building this semester. The hardware and algorithms form the foundation. Your math and machine learning act as the internal intelligence engine. Finally, software engineering and Java skills wrap around it to create the functional interface. You can use this structure to align your study schedule. For example, reviewing Cholesky decomposition from your math syllabus immediately before starting the corresponding machine learning unit creates a direct path from theoretical calculation to practical application. Pacing is critical. If you view the syllabus as a strategic roadmap rather than a collection of separate exams, you can see exactly how each unit supports the next. This semester provides the exact toolkit used in professional AI development environments. The workload is a preparation for the complexity of the industry. Mastering this interconnected stack transforms you into a capable AI engineer. You are no longer just passing exams, you are building the architecture of your future career.